Welcome to AI Paper Podcasts, the show where we distill complex research papers into, well, actionable insights and maybe some surprising facts.
Hopefully some useful ones.
Exactly. Today, we're diving into a paper that honestly unveils a true breakthrough, Minimax M1, scaling test time compute efficiently with lightning attention. This is, get this, the world's first open-weight, large-scale hybrid attention reasoning model. And it's making waves for a very good reason.
It really is.
Minimax M1 combines a hybrid mixture of experts, MoE architecture, with a pretty groundbreaking lightning attention mechanism.
Score combo.
And the headline features are just, well, astonishing. It natively supports an incredible context length of 1 million tokens.
1 million.
That's 8 times the context size of something like DeepSeek R1.
Huge difference.
And not only that, but it drastically cuts the computational cost. It uses only 25% of these FLPs, that's floating point operations, the standard compute measure, compared to DeepSeek R1 when generating 100K tokens.
Which is a massive efficiency game at scale.
And it was trained using a novel reinforcement learning RL algorithm called CISPO. Apparently, this dramatically boosted efficiency, letting them finish training in just 3 weeks on 512 H800 GPUs. Costs around, $534,700?
Yeah, roughly that, which for this level of model is actually quite efficient resource-wise.
For the result, a model that really shines in complex software engineering, tool use, and those super long context tasks. It feels like it's setting a strong foundation for the next generation of language model agents, the ones tackling really complex real-world challenges.
I think what's truly revolutionary about Minimax M1 is how it redefines the practical limits, especially for open weight models.
Right.
It's not just about making a bigger model, it's pioneering an architecture that lets the AI genuinely think and reason over huge amounts of info for longer, without the costs becoming completely prohibitive.
Oh, okay.
And that's what unlocks totally new application spaces for these models.
That's a crucial distinction then. So when we talk about its, immense capabilities, what does Minimax M1 actually look like under the hood? What are the core architectural bits and the sheer scale that makes it different?
So at its heart, Minimax M1 builds on their previous model, Minimax Tech 01. And yeah, it's positioned as the first open-weight, large-scale hybrid attention reasoning model.
Okay.
And when we talk scale, we're looking at 456 billion total parameters. But, and this is key, only 45.9 billion parameters are activated per token. So it's efficient in that way too.
Right, leveraging a mixture of experts.
Exactly, leveraging an impressive 32 experts within that MoE framework.
It's a lot of experts shipping in for each token. And this hybrid attention mechanism is really central, isn't it? How does that design specifically tackle the computational bottlenecks we always hear about with LLMs?
It's a very clever setup. The architecture basically integrates a traditional transformer block, the kind with softmax attention, after every 7 of these transnormer blocks.
Transnormer blocks, okay.
And those use their novel lightning attention.
Gotcha.
The beauty here is, while traditional softmax attention has that quadratic computational complexity, right? It scales really badly with sequence length.
Yeah, the n-squared problem.
Exactly. That's why models usually choke on really long reasoning tasks. By strategically weaving in these linear attention variants in the transnormer blocks, they've found a way to sort of bypass that fundamental quadratic cost. It makes long context processing actually practical.
So lightning attention, it's not just marketing speak. It's the real engine driving this efficiency. How does this IO-aware linear attention thing fundamentally change the game for test time compute? The actual cost when you're using the models.
It's absolutely critical. Lightning attention is, like you said, an IO-aware implementation of a linear attention variant. It's designed precisely for efficient scaling of test time compute.
Right.
What that really means is, as the model processes longer and longer sequences or gets into more complex reasoning, the computational load doesn't just explode quadratically like it used to. And that efficiency is what allows Minimax M1 to be realistically used for real-world applications that need these very long, extensive reasoning processes without needing, a whole supercomputer for every single query.
And the numbers really make that clear, don't they? Can you give us a sense again of just how much more efficient M1 is compared to, say, DeepSeek?
The difference is pretty substantial. M1 uses less than half the FLOPs at a 64K token generation length.
Wow, less than half.
Yeah. And it drops to roughly 25%, so only a quarter of the FLOPs, at 100K token length compared to DeepSeek R1.
A quarter.
Yeah, it's not just a small tweak, it's a really foundational shift in the cost-performance equation for these long context models.
And then there's the context length itself. Native support for up to 1 million tokens.
Yeah.
This is just genuinely astounding.
Yeah.
How does that compare, put it in perspective, against other big models, even the closed source ones?
It truly sets a new bar, especially for open weight models. Like you said, 8 times the context of DeepSeek R1. That's an order of magnitude bigger than almost all other open weight large reasoning models out there today.
An order of magnitude.
Yeah. And if you look at the paper's comparison table, Minimax M1 80K supports 1 million input tokens and up to 80,000 output tokens.
80K output, that's also huge.
It is. Contrast that with, say, OpenAI's O3, that's 200K input, 100K output. Claude 4 Opus is 200K input, 32K output. Gemini 2.5 Pro hits the 1M input mark, but its output is capped at 64K.
So M1 is right there at the top for input and really pushing long output generation too.
Exactly. It's leading the open models on input and pushing boundaries on output length.
This brings up a really important point. Why should you, the listener, care so much about these huge context lengths and efficiencies? What kinds of problems does this unlock that were maybe just out of reach before?
Well, the ability to actually process 1 million tokens and generate such long, coherent responses, it fundamentally changes the types of tasks AI can tackle.
Like what, specifically?
Think about debugging massive, really complex code bases, or analyzing incredibly lengthy legal documents, contracts maybe, or even sifting through like years of research papers to synthesize genuinely new insights.
Right, things where you need to hold a lot of information in mind.
Exactly. It means Minimax M1 is exceptionally well suited for problems that require deep, continuous engagement with information and that extensive step-by-step reasoning. It lets the model maintain a complete thought process across a much, much broader scope than before.
Okay, so they built this incredibly capable architecture, fantastic, but how did they actually get it to this point? The paper talks about a fascinating training journey, starting with continual pre-training. Can you walk us through that foundation first?
Sure. They kicked things off by continually pre-training their previous model, Minimax Textera 1, on an additional 7.5 trillion tokens.
7.5 trillion, wow.
Yeah, a massive amount. And crucially, this wasn't just random data scraped off the web. It was a meticulously curated, reasoning-intensive corpus.
Okay, so quality over just quantity.
Definitely a focus on quality. They refined their web and PDF parsing, had enhanced cleaning rules, and put a strict emphasis on extracting natural question-answer pairs. And interestingly, they explicitly avoided synthetic data at this pre-training stage.
That's a strong choice. Why avoid synthetic data there?
Seems like they wanted to build the core capabilities on real-world patterns first. They also significantly increased the proportion of STEM, code, book, and reasoning-related data up to about 70% of the mix.
Okay, really leaning into the reasoning aspect, and I heard they extended the context length during pre-training quite carefully in stages, not just one big jump.
Exactly right. They did it smoothly across 4 stages. Started at 32K tokens and gradually worked their way up to the full 1 million.
Why the staged approach?
It's particularly important for these hybrid architectures like Minimax M1. It helps to mitigate potential issues like sudden gradient explosions or general instability that can sometimes happen if you just abruptly increase the context length by a huge amount. It lets the model adapt more gracefully.
Makes sense. So after that massive pre-training foundation, they moved into supervised fine-tuning, SFT. What was the goal there? What kind of data did they use?
Right, SFT was all about instilling specific desired behaviors and, importantly, reasoning patterns. They focused heavily on teaching the model reflection-based chain of thought.
Reflection-based 2ST. So thinking about its own thinking.
Kind of, yeah. Using high-quality examples to teach it how to self-correct, pause, reconsider, basically, reason more deeply. And a huge chunk, about 60% of the SFT data, was specifically math and coding sample.
Setting the stage for the hard stuff.
Precisely. It laid a very strong foundation for the next big phase, reinforcement learning.
And the RL stage really seems to be the absolute core of M1's development. But I imagine even with the efficiencies of hybrid attention, training RL at this kind of scale must have had its own unique challenges. What were the sort of headline stats for this RL push?
You're spot on. Even with architectural help, scaling RL this far definitely presents new hurdles. But impressively, the Minimax team managed to complete the entire RL run for Minimax M1 in just 3 weeks.
3 weeks. That's fast.
It is, considering the scale. They used 512 H800 GPUs. Now, that's obviously significant compute.
Sure, not insignificant.
But for the capabilities they unlocked in an open-weight model, that estimated rental cost of around $534,700 US actually represents a pretty efficient path to getting near-frontier performance.
That is remarkable in that time frame. Okay, now this brings us neatly to their novel RL algorithm, CISPO. You mentioned earlier that existing methods like PPO and GRPO kind of struggled. What was the specific problem they ran into with those standard algorithms in their hybrid setup?
Yeah, the issue they pinpointed was quite interesting. Initial experiments just using the hybrid architecture without any specific RL tuning yet showed that GRPO was actually hurting training performance.
Hurting it.
It was failing to promote the long chain of thought reasoning they awarded. The core problem was the clipping operation in both PPO and GRPO loss functions.
The clipping. That's usually for stability, right?
Exactly. It's designed for stability. But in this case, it was unfortunately clipping out rare but really crucial reflective behaviors.
What do you mean by reflective behaviors?
Think about phrases like, however, or let me recheck that, or wait, or even huh. These little markers of deeper reasoning, which are often statistically rare but vital for complex problem solving.
They were getting clipped.
They were getting clipped out and basically prevented from contributing to the gradient updates, so the model wasn't learning from its own best reasoning moments effectively. They mentioned even DAPO, which tries to loosen the clipping bound, didn't really work well in their specific setup either.
Okay, so standard methods were accidentally throwing out the baby with the bathwater, essentially.
You could put it that way, yeah.
So CSP clipped IS weight policy optimization is their fix. How does it work differently? You said instead of clipping token updates, it clips the importance sampling weights.
Exactly. It sounds subtle, but it's a really impactful distinction.
How so?
This approach means it explicitly avoids dropping tokens from the gradient calculation, even if those tokens represent a large update signal. This helps maintain entropy, ensures more stable exploration during training,
Okay.
and crucially, by preserving gradient contributions from all tokens, it's much better suited for training models to generate those really long, coherent responses where quality needs to be consistent throughout.
And they back this up with results.
Oh, yeah. Their empirical validation is pretty compelling. They ran a controlled study using Qwen 2.532b models on the AE 2024 benchmark. CSP achieved a 2x speedup compared to DAPO.
Twice as fast.
Twice as fast. It matched DAPO's performance using only half the training steps. That represents a significant efficiency gain for doing large-scale RL. You're effectively having the compute needed to reach a certain performance target.
That's a genuine game changer for training these huge models.
Yeah.
But okay, even with CISPO and the inherent efficiency of lightning attention, training at this enormous scale must have thrown up other weird roadblocks. One mentioned was a computational precision mismatch. What was going on there?
Yeah, that was a tricky one. They noticed a significant difference, a discrepancy in the token probabilities the model was outputting when it was in training mode versus inference mode during RL.
And that mattered because...
Because it actively prevented the reward signal from growing. The model wasn't learning properly because its predictions were inconsistent between training and evaluation.
Huh. What caused that?
They traced the root cause to high magnitude activations happening right at the end in the LM head, the final neural network layer that predicts the next token.
And the fix?
Quite elegant, actually. They just increased the precision of that LM output head to FP32, 32-bit floating point.
Higher precision.
Yep. And that successfully realigned the probabilities. The paper has a figure 3, showing the correlation jumped dramatically from around 0.9 up to like 0.99 after they made that change.
Simple fix, big impact. Okay, another challenge they hit was optimizer hyperparameter sensitivity. Sounds like the standard AtomW settings just didn't work.
No, apparently the default EDA1-2A led straight to non-convergence. The training just wouldn't stabilize.
Why not?
Well, imagine dealing with gradient magnitudes that span an enormous range from like 1E18 all the way up to 1E5, just wildly different scales.
Wow. Okay.
And add to that weak correlation between the gradients in adjacent training iterations. It created a really, really tricky optimization landscape.
So what did they have to do?
It required very specific, careful tuning of those AtomW hyperparameters. They landed on Lydia11 is 0.9, YE2 is 0.95, and EPS equals 1E15.
Very specific numbers.
It really highlights just how sensitive these massive training runs can be. Pushing the boundaries often means getting deep into these practical, granular tuning details.
Definitely sounds like it. And then there was the issue of models sometimes generating pathologically long and repetitive responses. That sounds like a potential nightmare for training stability.
Oh yeah, that can completely derail things. If the model gets stuck in a loop generating junk, it can produce huge gradients that threaten the whole model's stability.
So how did they stop that? Their fix was early truncation via repetition detection.
Exactly. A fairly simple but effective heuristic rule. They decided to just halt the generation process if they detected 3,000 consecutive tokens, where each token had a predicted probability above 0.99.
Ah, so if it's super confident about the same sort of thing for too long, just stop it.
Basically, yes. It successfully prevents that instability from those pathological loops, and as a side benefit, it also improves the overall generation throughput by cutting off those unproductive repetitive cycles early. It's a neat example of practical engineering complementing the core algorithmic advances.
Makes sense. Okay, so they handled the architectural challenges, the RL algorithm, the training stability issues. What about the actual data they used for the reinforcement learning? They emphasized a diverse data and curriculum. Sounds complex.
It was definitely comprehensive. They broke it down into two main categories. First, reasoning-intensive tasks where they could use rule-based verification for the reward signal.
Rule-based, so more objective feedback. Like math.
Exactly. Mathematical reasoning was a big one. They had nearly 50,000 high-quality competition-level math problems, meticulously cleaned, deduplicated, filtered to ensure they were challenging but still learnable, and importantly, making sure there was no overlap with SFT data or evaluation benchmarks.
Got it. What else fell into rule-based?
They also synthesized about 53,000 logical reasoning samples covering 41 different task types, things like ciphers, Sudoku puzzles. They used their own framework called SynLogic for this, which even had dynamic difficulty adjustment. And for competitive programming, they collected 30,000 problems from online platforms, even using another LLM to generate test suites where they were missing, again, filtering for quality and moderate challenge. This whole set provided a really strong, grounded foundation in verifiable reasoning.
Okay, now this next part sounds particularly exciting for real-world impact. Software engineering. They used actual GitHub issues and pull requests.
Yes, this is really innovative. They set up verifiable RL environments using real-world GitHub data for tasks like bug localization, code repair, and test case synthesis.
How did they get the reward signal? Just checking if the code compiled.
Even better, they used a sophisticated containerized sandbox environment. The model's generated code was actually executed in the safe sandbox, and the reward was directly based on the execution outcome, essentially, the pass-fail status of relevant tests. That's direct real-world feedback on whether the code works.
That is incredibly powerful for training practical coding skills.
Okay.
So that's the rule-based side. What about the general domain tasks where rules are harder to apply?
Right. For those, they relied more on model-based feedback. For tasks that still had a ground truth answer, like certain STEM problems, but where writing a rule to check it is hard.
Yeah.
They used what they call a generative reward model, or GenRM. This model assigned a reward score on a 5-grade scale, and it was trained using human annotated benchmarks.
Okay, using another model is the judge. And for tasks with no ground truth, like creative writing or general instruction following.
There, they used a pairwise comparison framework. The model's response was compared against an internal reference answer and scored simply as better, mat a 1, same, 0, or worse, 1, 1. They also still incorporated rule-based rewards where possible for things like adhering to specific constraints in the prompt.
Now, one challenge you hear about with these generative reward models, especially for long chain of thought, is a potential length bias, right?
Right.
Where the reward model starts preferring longer answers, even if they're just verbose nonsense.
Yes, that's a huge potential pitfall. They explicitly mentioned this. The GenRMs initially did prefer longer outputs, which can lead to the RL policy learning to just be wordy to hack the reward rather than actually improving quality.
That sounds like a fundamental problem for optimizing the actual policy. How do they tackle that bias?
This was critical. Their main solution was continuous online monitoring of this length bias throughout the RL training process.
Online monitoring, so watching it in real time.
Exactly. If they detected that the reward model was starting to drift towards favoring length over substance, it triggered an immediate recalibration of the GenRM.
Ah, a feedback loop for the reward model itself.
Precisely. And complementing that, they also use several RL-SI techniques, things like reward shaping, value clipping, and normalization, specifically designed to make the reward signals less sensitive to superficial characteristics like length, and instead focus the optimization pressure on substantive quality. It's a pretty sophisticated, multi-pronged approach.
That's incredibly clever. It really shows the depth of engineering needed. And to bring all this incredibly diverse data together, the math, the code, the GitHub issues, the general tasks they used, a carefully managed curriculum, right? How did they structure the training flow?
Yeah, the curriculum was key. They started the RL training primarily focused on those reasoning-intensive tasks, the ones with the reliable, rule-based rewards. Build that strong foundation in verifiable skills like math and coding first.
Makes sense.
Then they gradually started mixing in the general domain tasks, the ones relying more on the Gen RM feedback.
Why sequence it like that?
The main goal was to prevent catastrophic forgetting. You don't want the model to lose its hard-won specialized skills in math or code when it starts learning the broader, more open-ended tasks. This gradual mixing ensures it continues to refine those verifiable skills while also progressively enhancing its performance on diverse general tasks like instruction following and general phenia.
Right, balancing specialization and generalization. Okay, so they built a solid 40K token model using this process. But the Minimax team didn't stop there. They scaled up to what they call longer thinking, pushing the RL training all the way to 80,000 tokens for the Minimax M180K model. How did they adapt the data for those significantly longer sequences?
They actually used the performance of the 40K model to guide the data filtering for the 80K stage. They removed samples the 40K model found easy and specifically favored more challenging math and coding problems.
Okay, upping the difficulty.
Exactly. And here's a crucial insight. They actively downsampled the synthetic reasoning data at this stage.
Downsampled. They used less of it. Why?
Because they observed that, while useful earlier on, that synthetic data tended to lead to more repetitive and homogeneous outputs when generating really long sequences. It actually proved detrimental to the stability of long context RL training.
Interesting. So sometimes less of a certain data type is actually better for pushing performance at the high end?
It seems so in this case. It's a great example of the practical nuances you discover when scaling things up this far.
And they also had a staged length scaling strategy again, right? Incrementally going from 40K up to 80K.
Yep, step by step. From 40K, then to 48K, 56K, 64K, 72K, and finally reaching the 80K token output length.
What signals told them it was okay to move to the next stage? How did they know the model was ready?
They relied on empirical indicators, things like checking if the perplexity on the generated sequences had converged, meaning the model was stable at the current length. They also looked at the 99th percentile of the output lengths. When that started approaching the current context window limit, it suggested the model was capable of using more length. These metrics help them make data-driven decisions about when to bump up the context window.
Smart. Now, during the scaling process, they also hit another type of training instability they call pattern collapse. Yeah. Sounds ominous what was happening.
Yeah, apparently in the later stages of training within each length window, they noticed the model starting to degrade. The latter portions of the really long generated sequences would just devolve into incoherent text, and the perplexity in those sections would shoot up.
Pattern collapse.
Uh-huh.
Okay. What was causing that?
The root cause seemed to be that the negative training samples, the ones the model should learn not to generate, were increasing in length much faster than the positive samples.
Okay.
This led to disproportionately large negative gradients accumulating specifically in the later segments of the sequences. They link this partly to how GRPO normalization works.
So how did they fix this pattern collapse issue?
They implemented 3 key solutions together. First, actively detecting those repetitive patterns using the early stopping heuristic we discussed earlier.
Right, stops loops.
Second, they adopted a combined loss approach using both sample-level loss and token-level normalization, which seemed to help balance the gradients better. And third, importantly, they actually decreased both the gradient clipping threshold and that Ushi parameter from CISP. Basically, being a bit more conservative with large updates in these very long sequences, these adjustments together were vital for maintaining stability at those extreme 80K context lengths.
Wow, the amount of tuning and problem solving required at this scale is just incredible. So after all this innovation, all this hard work, what does it actually translate to in terms of cold, hard performance benchmarks. How does Minimax M1 stack up against the competition, especially other open weight models?
Well, the overall picture is that Minimax M1 firmly plants itself among the world's best open weight models. It's genuinely comparable to other giants like DeepSeek R1 and the recent Qwen 3 235B.
Okay, playing in the big leagues.
Absolutely. And when you dig into the specific benchmarks shown in the paper, its particular strengths become really clear.
Right, let's unpack those strengths. For software engineering, using the SW Bench Verified benchmark, Minimax M1 80K gets a very solid 56.0%. You mentioned it's slightly below the very latest DeepSeek R1, but
But it significantly surpasses other open weight models, and they largely credit this to those unique execution-based RL environments we talked about. That direct, real-world code execution feedback seems to make a big difference for practical coding ability.
makes sense. Then for long context tasks,
Yeah.
this seems like it's home turf.
Oh, absolutely. This is where Minimax M1 truly shines, leveraging that massive 1 million token context window on benchmarks like OpenAI MRCR and Longbench V2. It doesn't just blow away all the other open weight models.
Yeah.
It actually surpasses strong commercial models like OpenAI O3 and Claude 4 Opus in several long context valuations. It ranks second globally on some, only behind Google's Gemini 2.5 Pro.
Wow, second globally behind Gemini 2.5 Pro on some long context tasks. That's huge for an open weight model.
It absolutely validates the immense value of that architectural design, the hybrid attention, the massive context window, and its ability to genuinely reason over these extremely long inputs.
Okay, what about agentic tool use? How well does it actually use external tools?
Also, very strong results there. On the TAU bench benchmark, the Minimax M1 40K model scored 60.0%. Impressively, that surpassed all other open weight models, and even Gemini 2.5 Pro on the specific airline booking subtask.
Beat Gemini 2.5 Pro on a tool use task.
On that particular subtask, yes. And the 80K model confirmed this strength, scoring even higher at 62.0%. So it's not just good at internal reasoning, it can effectively apply that reasoning to interact with external tools to solve problems.
That's really promising for building useful agents. And the paper also visualizes the effect of RL scaling, right? Showing improvement over time.
Yes, figure 4 in the paper is quite telling. It shows really consistent improvements during the RL training phase in both model accuracy on benchmarks and the average length of its responses.
So it got smarter and could think for longer.
Exactly. For instance, on the A 2024 math benchmark, accuracy climbed from around 68% up to 80%, while the average response lengths grew to exceed 20,000 tokens.
20,000 tokens on average. That's extensive reasoning.
It really is.
Yeah.
And it empirically backs up the core idea of the paper. The benefits of effectively scaling test time compute, allowing for longer, deeper reasoning. Now, while M1 might lag slightly behind the absolute bleeding edge commercial models, or maybe the very latest DeepSeek updates in some hyper-specific math or coding contests,
Sure, the field moves fast.
it remains highly competitive across a broad range of benchmarks, reasoning, knowledge, factuality, general assistant capabilities, especially when you focus on the open weight landscape. It's a top contender.
This really underscores their achievement, doesn't it?
Yeah.
They've managed to build an open weight model that can genuinely compete right at the frontier of AI capabilities, particularly in these complex, long-form, real-world scenarios.
Precisely. It's a remarkable step forward, especially for the open source AI community, offering this kind of power without being locked behind a proprietary API.
So wrapping this up, what does all this really mean for you, our listener, working in the AI and ML space? Well, Minimax M1 represents a truly groundbreaking, open-weight, large-scale reasoning model. It's uniquely positioned by that lightning attention architecture and the really significant efficiency gains they got from their CISPO algorithm.
Yeah, that combination is key.
Its massive context window, that efficient test time compute we talked about, and its proven strength in really complex real-world tasks like software engineering and tool use, it genuinely feels like it establishes a strong foundation for the next wave of language model agents.
I agree. And Minimax AI themselves, the creators, they envision these kinds of efficient, long reasoning architectures driving things like automation within company workflows or maybe accelerating scientific research.
Right, especially for tasks needing agents that have to interact over dozens, maybe even hundreds of turns.
While seamlessly integrating huge amounts of information from that long context history. That ability to reason extensively and efficiently is just absolutely crucial for those kinds of complex, multi-step future applications we're all thinking about.
Definitely. So that brings us to our final thought for you to mull over. Given these incredible advances we've discussed, scaling reasoning capabilities, massive context lengths, improved efficiency. What new, previously maybe unsolvable real-world problems do you now envision are truly within reach for large language models, perhaps even for the very first time, thanks to models like Minimax M1?
It's an exciting question to ponder.
It really is. And if you want to explore the models yourself, they are indeed publicly available. You can find them on GitHub and Hugging Face. There's also commercial API available at minimax.io if you want to try it out that way.